For the very loud voice. So
No, but for the recording. Okay. Only for the records.
Okay, let me just hold it.
Okay, welcome everybody after the lunch. It's become normal, traditional to have a couple of anecdotes about our two heroes and the state of Israeli physics in general before we start. So I'm going to follow this very recent tradition. And I start way back in 1963, the Scottish University summer school, when I was very young, full of physics ideas, didn't know anything about administration. That was for old, boring men. When I met a lot of Israeli physicists, several of whom I've met in the past couple of days, and got a very strong impression that long time ago about just the state of Israeli physics. You know, it had a bit of aggression, had full of ideas, a lot of bright young people, very positive impression. And I'll come back to the Scottish summer school at the end. Lenny referred this morning to Israel as a model for the world, and particularly referred to, shall we say, developing countries. I've recently taken a job in Scotland to get 6 physics departments to work together. They've been fighting each other for a couple of 100 years. Let me make you, just to reveal the extent that Israeli physics is in people's heads. I mean, I did sit down one night and say, along with my wife did not believe this would ever work, so I had a certain resistance. I sat down with a list, and I came with a list was, why did Israeli theoretical physics work? You know, and it was a lot of energy, a lot of dynamism, a lot of aggression, huge openness to the world, both with people coming to Israel, people going out of Israel, and just total engagement. And I ended up sitting there before I signed my contract, pretty lucrative contract, but nonetheless, would it happen? And the question, I ended up posing to myself, just how insidious, as I said, the Israeli physics style is. Could I make this happen in Scotland? And I thought, it's going to be pretty hard. And it makes you realize just what the achievement is when you have to think similar thoughts for yourself in a slightly different context. And that reminded me of an anecdote. So this is an anecdote about Maxwell. And it's also a sort of a cautionary tale about how do you build good physics. So first of all, the University of Aberdeen made a very good early move. They hired Clerk Maxwell at age 22 into a chair. The next move was over to Clerk Maxwell, which I thought was very percipient. He married the Vice-Chancellor of the university's daughter. And so you thought, well, he's got it made. But he didn't pay attention to politics. There happened to be 2 universities in Aberdeen, and they were about to merge. And the rule was last in, first out. No argument about skill or whatever, so they fired Clerk Maxwell at age, I forget, 26 or something. So there's a certain tradition in Scotland about how not to do it, shall we say. Okay? Which also makes you realize just what skill sets you need to really make it happen. So I very much take my hat off to Israeli physics and, as I said, to our 2 heroes. I'm afraid at this point I will be a little bit Eliezer biased, which is an anecdote about A, the Scottish University summer school, and B, your winter school, which has happened over the past couple of years. Both of these schools, along with Lesush and the Cargé school, used to be funded by NATO, and NATO pulled the rug. Right? So this is a threat to all of these schools. So you'd expect me sitting in a research council in the UK to hear about this first from the Scottish people. Wrong. First people on the phone, Eliezer. So you're moving fast, you keep moving, you have a very good intelligence system, and also the crucial thing, and this sounds like a little bit like boasting, but it's really a statement about Eliezer. I was in charge of the British Funding Agency and was about to move to the European Science Foundation, and it was clear there should be a solution in there somewhere. So not only did he know first, He knew which button to press, and he pressed it very efficiently, very politely, very effectively. We came up with a very mutually advantageous solution for the Scottish University Summer School, the Winter School here, for the European Science Foundation, small local difficulties in France, but I believe that too will be solved. So a message from the past and whatever. These guys are really slick operators. Right? So with that, I will stop. First of all, what you've achieved is not easy. It can really go wrong very quickly, very easily. It requires a lot of energy and skill. And I think both in the past, going back to the 1960s and right up to the modern days, you're doing it very well. And in particular, our two heroes are doing it very well. So with that, we go to this afternoon's action. So Ofer will give us a talk, and let me read out the title, which is, if I can find it, String Theory for Large N-Gauge. Well, it's here. Over to you.
Okay, thanks. So I would like to start by thanking both Eliezer and Shimon for everything that they've taught me throughout the years in numerous uncountable discussions, and of course, especially Shimon, who taught me a large part of what I know when I was a student. And we've already heard a lot about Shimon and we'll hear more, I'm sure, about Shimon as a physicist and as a person and as a leader of the Israeli high-energy physics community. But we haven't heard yet about Shimon as an advisor, so I would like to maybe highlight two non-trivial features of Shimon as an advisor. So the first one is his devotion to his students, and I can give an example of that already from the first time that I met Shimon, which is when I was one of many students in his field theory class 16 years ago. And this was during the time of the First Gulf War, which I guess looks like prehistory now. And but because of the war, I was in the army at the time, so I couldn't take the regular exam in the course. And there was a special examination period for soldiers. And it turned out that I was the only student in the course who was taking this special exam in field theory. And I remember that Shimon not only prepared a beautiful exam just for me, and I think, if I remember correctly, that exam is the first time that I encountered the large N expansion, which will be the subject of my talk today. But also I remember that that's also true, by the way. But I also remember the exam was actually here in this room, and I remember that throughout most of the exam, Shimon was standing above my shoulder and reading what I was writing and making sure that I was heading in the right direction. So, and that sort of close guidance, of course, has continued throughout the time that I was Shimon's student, so I'm very grateful for that. And the second feature is, of course, Shimon's enthusiasm always to learn new things and to work on the latest exciting new developments. And of course, that's useful for any physicist, but I think it's especially useful for an advisor because it enabled me to be exposed to many different things in my career as a student. So I already apologized to Shimon that in this talk I couldn't find anything that's exciting and new that would also be appropriate to talk about here. So instead of that, I'll give more of a review talk of what we've learned about string theory for large N-gauge theories in line with the title of this conference. And of course, as usual in these sorts of talks, I'll talk about achievements and perspectives, and the achievements will almost all not be my own. Many of them will belong to various people in the audience here. And the perspective, on the other hand, will be my own, so people who have other perspectives are welcome to make comments and argue. And the theme of this talk will be to try to unite the works of Shimon and Eliezer. So, well, I won't try a grand unification of everything because, well, I tried, but I failed. So I'll try just to unite some lectures that Shimon gave and some lectures that Eliezer gave. So I'll try to unite lectures that Shimon gave, actually, I think in Scotland, 25 years ago about phases and gauge theories, and lectures that Eliezer has been giving in the past years about phases of gravity. And, of course, we know now that the phases of gauge theories and the phases of gravity are closely related to each other. And I'll start by an introduction describing how that relation works. And I'll then give various examples of that relation, discussing first the phases of pure gauge theories and other theories that have only adjoint matter field, and then we'll see what happens when we add also flavors. So the relation between gauge theories and string theories was described already yesterday in Gabriela's talk. So 't Hooft showed back in 1974 that if we take the Large-N limit of an SUN gauge theory, keeping fixed the 't Hooft coupling, or equivalently keeping fixed the QCD scale, and also keeping fixed the number of flavors in the Large-N limit, then this gives us a string theory with a string coupling that goes as 1 over n, and so the string theory becomes weakly coupled in the Large-N limit. And 't Hooft showed that just the Feynman diagrams mapped more or less 1 by 1 between diagrams in a field theory and diagrams in a genus expansion in string theory. And now there's accumulated evidence that this type of relation also goes way beyond perturbation theory. But even just from perturbation theory, we can learn various features of this type of relation between gauge theories and string theories. We see that if we have an SUN gauge theory with only adjoint fields, then we get the dual string theory as a closed-oriented string theory. And there are simple generalizations. If you have an SON or an SPN theory, you get closed unoriented strings, or strings in orientifold backgrounds. And similarly, for SUN theories with matter in symmetric or antisymmetric representations, we also know how to describe those through closed unoriented strings. And if we also have fields in the fundamental representation, then they give us open string sectors. In these Feynman diagrams, they give us boundaries of the world sheet. And we know that we have to have one open string sector for every type of flavor in the fundamental representation. And in the module language, that means that our string background has to include one Dbrane for every field in the fundamental representation. So that's the general relationship. And through this relationship, we can map phases of gauge theories, at least of gauge theories that have a nice Large-N limit. We can map them to phases of string theory. Of course, we don't get generic backgrounds of string theory in this way, but every gauge theory gives us some background of string theory. And of course, string theory always includes gravity, so this gives us a mapping to phases of gravity. And this mapping is generally, well, at least in many cases, it's sort of a strong weak coupling duality, so it's interesting in both directions. There are some cases where we understand the phases of gauge theories, and we can use that to learn about phases of gravity. And there are other cases where we understand phases of gravity and can use them to learn about phases of gauge theories. And in particular, in the Large-N limit, as I've said, the string becomes classical, it becomes weakly coupled, and also the gravity becomes classical, so it looks like we should be able to make progress in that limit. Now, in the past, there have been very few examples of this correspondence, even though, as I've said, it's supposed to be completely general. In the past, we only had very few examples of this. There was the example of matrix models corresponding to C less than or equal to 1 strings, but that involved a somewhat different scaling limit. There were examples in topological theories, and there was the example of two-dimensional QCD, whose string theory was described by Gross and Taylor, but the relation of that to the usual string theories is not yet completely clear. So we didn't really have any complete examples, but that situation changed dramatically 10 years ago after Moldesena's ADS-CFT correspondence. And nowadays, we have lots of examples of this type of correspondence between large-N gauge theories and string theories, which are based on decoupling limits of Dbranes in string theory. So more or less any gauge theory we can construct on Dbranes in string theory. We can take some decoupling limit, and this gives us just a standard superstring theory, which is the stringy description of that specific large-N gauge theory. So there's sort of almost a prescription to build what's the string dual of a given gauge theory. And it seems like any theory that has a good Large-N limit, so in some sense any SUN, SON, or SPN gauge theory with appropriate matter fields, namely matter fields either in 2-index or 1-index representations, can be described by these methods, at least in principle. Of course, we don't really know exactly what the dual string is for many of these theories, but in principle it seems like there's no obstruction to building a standard superstring theory as the dual of these Large-N gauge theories. Now, one feature of these string duals that we find in this way is that they always have at least one extra non-compact direction in addition to the 4 dimensions that we live in, or, well, if it's a 4-dimensional gauge theory, otherwise whatever number of dimensions you have in your gauge theory. So there's always at least one extra direction, which corresponds in some sense to the energy scale in the theory. And in some cases, there are also additional extra compact directions, so that the details of that depend on the theory. Now, there are some very special cases where the dual string theory has a limit where it's weakly curved, and then it can be approximated just by classical general relativity or supergravity, which is sort of the simplest possible theory of gravity. Now, in order to have such a limit where the string theory is weakly curved and can be analyzed by the simplest gravity theories, well, this requires several strange features from the gauge theory. because, well, having a classical gravity approximation means that there has to be some separation of scales between the stringy excitations and the gravity fields. So the theory has to have a large gap between the modes that have spin less than or equal to 2 and the modes of higher spin, which is something that seems very unnatural in the gauge theory side. And similarly, there has to be a large gap to string excitations, so that if we're talking about a confining background, it must be that the string tension is much bigger than the characteristic scale of the mass gap squared. And again, that's a very strange feature for a gauge theory to have. And something that's perhaps even stranger is that we know that a string theory can only be weakly curved and stable, basically, if it's 10-dimensional flat space, because that's really the only weakly curved background that's stable that we know in string theory. So to have such an approximation, the theory must have some range of energies where it looks like a 10-dimensional a theory with 10 large dimensions and has a spectrum that's approximately supersymmetric and which is approximately 10-dimensional, mainly with the entropy going like the temperature to the 9th, which again, of course, is a very strange behavior for a 4-dimensional gauge theory to have. And, well, so this looks like an impossible list of features to demand from a gauge theory, but somewhat surprisingly, there are some gauge theories that actually satisfy these criteria, specifically maximally supersymmetric gauge theories when they're strongly coupled. So in particular, the 3 + 1 dimensional n equals 4 Yang-Mills theory in the limit of strong coupling satisfies these requirements. And as Schumann and his collaborators found, also other maximally supersymmetric theories in other dimensions have some range of energies where they're strongly coupled and where they satisfy all of these properties. So, so of course, it's nice to have these special cases where the dual background is weakly curved and we can analyze it by simple gravity theories. But this, of course, the existence of this limit is very non-generic. And for generic theories, we would not expect to have any range of energies where these properties are all satisfied. And in particular, of course, for large MQCD, it does not seem likely that such a limit would exist because it's hard to imagine why the string scale would be much bigger than any other scale in the theory, given that the theory does not have any dimensionless parameters. So what can we do given this situation? So, well, the obvious thing to do is to try to make progress on strings in highly curved backgrounds, which are the duals of generic gauge theories. And it looks like also Ramon-Ronon fields are necessary to describe these string theories. And unfortunately, that's a very hard problem. So people have worked a lot on it in the last 10 years, but not much progress has been made. So, well, so that's an obvious direction to do. But in the absence of progress in this direction, we can also try to use the backgrounds which we do understand, namely these weakly curved backgrounds, to still draw some lessons about generic large M theories, like large MQCD. And so one thing we can do is we can study the phase structure in the limit where the gravity is weakly coupled and hope that the same phase structure will apply more generally and perhaps teach us something about QCD. And this so this seems like just a shot in the dark. Why would these two different limits have similar physics? But in some cases, this connection between these two different limits can be made more solid by finding theories that interpolate between one limit in which they're described by weakly coupled gravity in this large 10-dimensional space, and another limit where they correspond to QCD or supersymmetric generalizations of QCD. And there are several examples discovered by these people of theories that have such an interpolation. And the way that this works is that you choose to add some specific degrees of freedom to QCD at some mass scale m. And then once you do that, your theory now does have a dimensionless parameter, unlike QCD. And you can take this dimensionless parameter to be the 't-Hooft coupling at this mass scale m, where you add the additional degrees of freedom. Now, if this 't-Hooft coupling is much smaller than 1, then the coupling continues to run below that mass scale m, and you can forget about all these heavy degrees of freedom. And at energies over to the QCD scale, which is much smaller than m, you find just usual QCD, so you're happy. And if you choose your added degrees of freedom correctly, then in the opposite limit, where the 't-Hooft coupling at the scale m is much bigger than 1, then it turns out that you can have a gravity approximation and get a weakly curved 10-dimensional background. Of course, in that limit, the extra degrees of freedom mix strongly with the QCD degrees of freedom, and the mass gap is of order m. So the physics is certainly different from QCD, but you do have an interpolation as a function of this dimensionless parameter between these two limits, and then that certainly gives some hope that the phase structure might be similar in these two limits. And in some supersymmetric cases, you can actually prove that there's no phase transition between these limits, and then you can be on a more solid ground. In non-supersymmetric cases, you have to wave your hands to some extent, but still there is an obvious relation. So this concludes the introduction, and we'll now analyze various phases of gauge theories and see how they're realized in the dual string theories. Are there any questions or comments so far? Okay, so we want to study the phases of gauge theory, so we go back to Schimon's lectures from 25 years ago, and in Schimon's lecture we find what are the possible phases of pure gauge theories, which here means theories with only adjoint fields, and we find that there are three possible phases. You can have confinement, you can have Higgs, or you can have a Coolant phase. So we'll study each of these phases in turn. So the first phase is the confining phase, and that's sort of the most natural phase to have a stringy description. And in fact, trying to understand confinement and the confining strings that connect quarks and antiquarks was, of course, the initial motivation for the development of string theory. So this is the phase that's most obviously suitable for a stringy description, although we'll see that there are stringy descriptions also of other phases. In this phase, one characterizing feature of this phase is that we have an area law for the Wilson line, and the quark-antiquark potential is proportional to the distance between a quark and an antiquark. And in these string theory duals, the way that we describe a Wilson line is, so the Wilson line is some curve on some curve in the four-dimensional space, and we need to describe the Wilson line. We put in a string that ends on that curve near the boundary of this space, which I'll always draw up. So this u direction is the radial direction, which is this extra non-compact dimension that we always have in these string duals. And to describe a Wilson line, we put in a string that ends at u equals infinity on the curve which the Wilson line describes. So we know that the string dual had better give, well, so to have a string dual of a confining background, we need to get this linear quark-antiquark potential. And the way that we get this is that the string, so it starts by coming off from infinity, but it has to eventually stabilize at some specific radial position u0. And when it does that, then basically your potential is dominated by this segment where the string just goes straight, and obviously its energy is proportional to L, and given by the local string tension for a string that sits at this value of u0. And if your background has a good gravity approximation, then you can easily compute the string tension just from the Nabu-Goto action, and you find that the string tension is proportional to the square root of the product of the GXX and GTT components of the metric evaluated at this position where the string wants to sit. So this formula is specific to the case where we have a gravitational limit, but of course the same picture for confining backgrounds should be much more general and should apply also when we do not have a gravitational approximation. Now, of course, another important property of this phase is that the string cannot end in this phase, so it does have to just stretch along and give us the confining potential. So this, of course, raises the obvious question of why would the string want to localize at some specific value of u0? And there are various mechanisms for that. And a clue as to why that would happen comes from another feature of confining backgrounds, namely the fact that 't Hooft loops in these backgrounds should be screened. And in these string duals, the 't Hooft loop is described by a Dbrane. So just like the Wilson loop is described by some string that ends on some curve on the boundary, the 't Hooft loop is described by a Dbrane that ends on the curve given by the loop, again, on the boundary of the space. And this Dbrane can either just be a D string, which would be completely analogous to the Wilson loop, or it can be a dp brane, or if we have some additional compact directions, it can also be a dp brane that wraps some p-1 cycle and again gives us a string in the 4 dimensions plus this radial direction, so that the pictures are essentially the same. And because the 't Hooft loops must be screened, then this Dbrane has to end somewhere in the interior of the space in order to get the screening. And this can happen in at least two different ways. So one way in which it can happen is that if the 't Hooft loop is described by a dp brane that wraps a p-1 cycle, then it's possible that as we move in the radial direction, the size of that p-1 cycle can change, since we're sitting in some warped background with a curved metric. And it's possible that the size of that p-1 cycle shrinks to 0 as we go down to lower values of u. And this provides us with a smooth end of space at some value u equals u0. And then it's natural for the string to sit at that value, since it feels a force that pulls it downward. And this is the mechanism in which confinement is realized in the backgrounds of Witten, Malvasena, Nunez, and Kilbanov-Strassler. So that's one natural option with which to get confinement to work in string theory. And the other option that we know of is that the Dbrane, instead of just ending by having its smallest string to 0, it could also end on a Neves-Schwarz 5 brane, and that's the mechanism that holds in the Polchinski-Strassler background, and presumably also another example. And of course, this mechanism is somewhat problematic because Neves-Schwarz 5 branes are notoriously difficult to deal with in perturbative string theory. The string coupling diverges there, which means that the 1/n expansion does not really work as we expect. There are some coefficients of terms that go like 1/n that diverge. So this case is sort of a bad case for the large expansion. And as I mentioned, both of these, so these are the only possibilities that I could think of, although of course it's possible that there are also other possibilities. And both of these possibilities are realized in some examples in the gravity approximation. And so, and in both cases, we can have both this screening of dead hoof loops, and related to it, we can have the confining force, which in the first case is realized just by the string living at the bottom of the space. And in the second case, even though the space doesn't end at this NS5 brane, it still turns out that the strings are attracted to this NS5 brane. So they prefer to live there, and they have a finite tension there, which gives the confining force. Now this tells us that really some features of the topology of the space, namely which cycles shrink in the interior and which ones do not, are important as order parameters for these different phases. So you can see, for instance, that so of course, when we think of phases, we naturally want to think about order parameters, and we see here that there are some, even in the confining phase, there are distinct additional order parameters that are important for various properties of that phase, specifically which cycles shrink and whether we and how do and what causes the hoof loops to end. So there seems to be various topological order parameters that tell us whether cycles shrink in the interior or not. So an example of such an order parameter is if we have a circle that shrinks, we can always wrap a string around that circle, and then when the circle shrinks in the interior, then we can have a finite action configuration with a wrapped string so that we have a finite expectation value for the Wilson loop around that cycle, while if the circle does not shrink, then we have a zero expectation value for the Wilson loop. So that's an example of how we can map sort of a topological order parameter, namely whether a cycle shrinks or not, into a natural gauge theory order parameter, namely Wilson loop. And similarly also for these other cases where we have larger p-1 cycle shrinking, you can also find order parameters directly in the gauge theory, which would tell you whether these cycles shrink or not. And it seems like these order parameters are important for classifying the types of confining string backgrounds that we can have. Even though the description of these order parameters that I gave uses basically the geometry and the notion of cycle shrinking, seems like it depends on the gravitational approximation, where we really have a well-defined space-time, then it seems like these topological order parameters should also exist beyond that approximation, since, for instance, Wilson loops certainly exist also when we don't have a good gravity approximation. So it seems like similar order parameters should exist in any string theory that's dual to a large n-gauge theory. And it would be very interesting to classify all of these order parameters. And in particular, of course, they can be indicators of phase transitions when we try to do these interpolations between the gravity regime and non-gravity regime or any other interpolations. It's important to try to follow these order parameters since they can be indicators of phase transitions. And we'll see an example of that in a few minutes, where these types of topological order parameters indicate phase transitions which one might not otherwise suspect. Of course, in the QCD string itself, it doesn't seem that there are any order parameters of this type. We don't have any evidence for any extra compact directions in the QCD string, which raises the question of which class of these backgrounds does it belong to. That it's not obvious that there's any cycle shrinking in the background, so it's possible that in the QCD string we have to invoke some analog of NS5 branes for that hoof loop to end, and that would, of course, be bad news. Or the other option is, well, other options are that the QCD string could have hidden extra dimensions, or there could be some other mechanism for confinement, which is not one of the two mechanisms I've described. And so far, we don't really know the answer even to basic questions like that. So this concludes the discussion of the confining phase and some additional order parameters which should exist in this phase. The next phase on Schimon's list is the Higgs phase, where the gauge group is completely broken. So in this phase, of course, we don't have any confining strings. But it turns out that even though we don't have confining strings, so one might have thought that this phase is hopeless for string theory description, it turns out that we do still have good string dual descriptions for this phase. Of course, here I should remark that Eliezer and many other people in the audience have taught us that the Higgs phase and the confining phase are actually the same in QCD-like theories, so maybe I shouldn't describe them separately, but they only become the same when you have dynamical quarks that have an effect, and in the large n limit, the effects of dynamical quarks are negligible. So in this large n expansion that I'm talking about, there is a real difference between the Higgs phase and the confining phase, so that both of them have a stringy description, but these descriptions are somewhat different. Of course, in the Higgs phase, since we have a charged condensate, then the Wilson loop can be screened, which means that in this string dual, there must be a place for strings to end, namely there must be some Dbranes in the bulk. And on the other hand, in the Higgs phase, that hoof loops should not be screened, so there should be no place for these Dbranes that give us that hoof loop to end. So there has to be some Dbrane in the bulk, which the fundamental strings can end on to give us this screening of the Wilson loops. And in some cases, so of course, these order parameters are just related by electromagnetic duality to the order parameters I described in the confining phase. And in some cases, indeed, there is such a relation. So this having a Dbrane in the bulk in some cases is related by electromagnetic duality to having a Neves-Schwarz fibrane in the bulk, which is the phase that I described before. And as an example of a stringy dual of a Higgs phase, we can take the n equals 1 star theory of Polchinski and Strassler, which is just the n equals 4 theory, which I write here as an n equals 1 theory with a superpotential with 3 adjoint fields with a specific superpotential that gives us n equals 4 supersymmetry. And then you can deform this theory by adding mass terms to the 3 adjoint superfields in this way. When you do this, it turns out that there are many, already classically, there are many different vacua to this theory corresponding to many different solutions to the supersymmetry equations of dw by d phi equals 0. So these equations tell us that the commutator of phi 1 and phi 2 is proportional to phi 3 and so on for every permutations, which means that the phi I give some representation of the SU2 group. Again, I here goes from 1 to 3, so these are just 3 matrices. And in particular, there's one special vacuum where the phi I are just the n-dimensional representation of SU2, so the biggest representation that can fit into an n by n matrices. And this background, as Polchinski and Strassler found, is described just by having a d5 brane, which sits in a background that's asymptotically ADS5 cross S5. So this is an example of this feature of describing Higgs phases by close ring backgrounds that have Dbranes in them. And again, this should be a completely general feature. The next phase on Schimon's list is the Coolant phase. This phase actually doesn't always have a stringy description, although sometimes it does. So the Coolant phase is a phase where part of the gauge group is broken to some abelian factors. And one case is where an SUN is broken, say, to an SUN minus k times U1 to the k, with k very small. In such a case, we know that we do still have a stringy description, and these U1s just live on k Dbranes that move around in the bulk and give us these U1 gauge fields. So this type of phase does still have a good string dual description. But if this k becomes large, for instance, if we imagine completely breaking the SUN to an abelian subgroup, then it seems that there cannot be any good stringy description, because in order to, well, these U1 fields have to live somewhere, and it looks like they have to live on n Dbranes to realize all these U1 gauge fields, which are just free fields at low energy if we're in a 4-dimensional gauge theory. And when we have n Dbranes and the string coupling is of order 1 over n, then that means that the open string coupling is actually of order 1, so that it looks like there isn't really any good stringy description of phases like this. So this is, so these are phases that actually don't have a string dual, but it's surprising that almost all other phases do have a good stringy dual. And if we're in lower dimensions where these U1s are actually not free fields in the infrared, but they're confined, then we could still have a good stringy description even of these Coolant phases. And a simple example of that is just to consider any confining theory at finite temperature, or specifically at low temperatures. Of course, that gives us at low energies some 3-dimensional theory, which does confine U1 fields. And we know that in the low temperature phase of confining backgrounds, then the Polyakov-Susskind loops or the Wilson loops around the Euclidean time direction are 0, which means that the eigenvalues of these matrices are uniformly spread on the unit circle. So in this phase, the SUN is broken to U1 to the n, but we know that we do have a good stringy description of these phases just by putting the bulk string theory at finite temperature. So it looks like there's only a very small number of phases where we really don't have a stringy description, and even for these Coolant phases, in many cases, we can have a good stringy description. Of course, there are also many mixed phases, which I won't discuss here. You have oblique confinement phases, you have mixed Higgs Coolant phases, and so on. But it should be obvious how to generalize what I've said to those phases. Now, on Schimon's list, these are the only 3 phases that appear. But of course, since then, we've learned that we should add also another important phase of gauge theories, namely a conformal phase, where the gauge theory flows to a non-trivial conformal fixed point in the infrared. And again, you might think that this phase is not a stringy phase because it doesn't have a confining string. But again, we've seen in many cases that these phases can have good stringy descriptions. In such a phase, we have a conformal symmetry. So that implies that if we have a dual string theory, it has to live on a d+1 dimensional anti-de Sitter space, perhaps together with some additional compact dimensions. And whenever you have that, then the geometry automatically reproduces a quark-anti-quark potential that goes as 1 over L as dictated by the conformal symmetry. Unfortunately, conformal phases are more complicated, and we don't really know what the rules are for when, if we have some given theory that flows to a conformal fixed point, we don't know yet what are the rules for when such a phase is stringy and when it's not stringy. It's clear that one necessary requirement for a conformal phase to be stringy is that the number of degrees of freedom has to be of order 1 over d string squared, like in any string background, which means that it should scale as n squared. Now, it sounds trivial that a large n-gauge theory would have a number of degrees of freedom go like n squared, but in fact, when you float it infrared, in many cases, the number is actually reduced, like in the infrared theory living on d2 branes or d1 branes, where the number is reduced to n to the 3/2 or n. And in those cases, we know that we don't have a good stringy description of the infrared limit. So this is obviously a necessary requirement to have a good stringy description of the infrared, but we don't really know what else is needed. For instance, if you take Young mills with 5 adjunct fermions, which is a theory for which one might argue that there is probably some fixed point in the infrared of the type discussed by Banks and Sachs, then it's not obvious if such a theory has a stringy dual or not, and that's still an open question. Now, in all the phases that I've described so far, there's been a lot of string theory, but the gravity has been quite boring. We just had some string theory moving in some curved background. Well, n-cubed is not a gauge theory at all. So I'm here talking just about gauge theories, and n-cubed is a completely separate, interesting question. So far, we've had various interesting effects in string theory, but the gravity side of things has been quite boring. Again, we just had strings in curved space with some solitons inside them. Things become more interested if we turn on finite temperature and we move over to the deconfined phase. And again, at first sight, the deconfined phase shouldn't be stringy because it doesn't have a confining string in it. But it turns out that these phases are in fact described by black hole backgrounds. And there are many different ways to see that. One way is that the deconfined phase is characterized by the fact that the Polakov-Susskind loop should be non-zero. And so this is a Wilson loop around the Euclidean time circle. And for this to be non-zero, it must be the case that this Euclidean time circle shrinks somewhere in the interior of space, which means that GTT goes to zero somewhere, so we must have a horizon. So this is more or less a derivation of the fact that a deconfined phase has to have a horizon somewhere. And similarly, we know that the string tension should vanish. So according to this formula that I wrote before, that means that GTT again should go to zero, and we should have some horizon. Another aspect of this is that we know that the free energy in the deconfined phase should be of order n squared, and we can get that in black hole backgrounds just by computing the classical free energy of black hole backgrounds, a la Gibbons and Hawking. And another feature is that we know that in deconfined phases, we expect to have a continuous spectrum of low energy excitations of the gluon plasma, and that is mirrored by the excitations around the black hole horizon, which again are continuous. So these are all strong arguments for this mapping between the deconfined phase and the black hole. But one final argument is that each of these phases is the generic phase at high temperature. So we know that in high temperature gauge theories, we always eventually go over to a deconfined phase. And similarly, when we have a gravity theory and we raise the temperature, we eventually collapse into a black hole. So again, that's another aspect of this general matching between deconfined phases and black holes. Now, these black holes, they fill all of the spatial directions of our theory, and they sit at some, well, the horizon sits at some position in this radial direction, say UH, and then the black hole may or may not fill additional directions, so that depends on the details of the background, which additional directions we have, and so on. And so again, we have various topological order parameters of this type, which are related to the question of whether various compact cycles in the geometry shrink or do not shrink at the horizon. Now, we can look at some simple backgrounds of the type of these backgrounds that I mentioned before, the Klebanov-Strasser and other backgrounds. The simplest backgrounds are ones where the geometry only depends on a single radial coordinate. And if we have a background like that, then we know that any extra cycles in the geometry cannot shrink at the horizon when we have a gravitational approximation. This is because we know that at the horizon the Euclidean time circle shrinks, and one cannot have a smooth geometry where at the same point we have both the circle shrinking and some additional cycle shrinking. So this simple argument already tells us that, at least in these simple cases, we cannot have any extra cycles that shrink at the horizon. Now, on the other hand, if we take one of these theories that I discussed before, where we have an interpolation between a QCD regime and a gravity regime, and consider that theory in the limit where it really gives us QCD, namely the weakly coupled limit, so in that phase, we expect that these topological order parameters, which are associated with these compact cycles, should not change in the deconfinement transition, because these order parameters are related just to the degrees of freedom involving this compact space, and they're all supposed to decouple in the QCD limit. So in this limit, we expect, because we know that in the confined phase, we have some cycles that do shrink at the horizon, then we know that the deconfinement transition should not change that. So it seems like in all of these cases, the topological order parameters are actually different if we look at weak coupling and strong coupling. Namely, at weak coupling, again, the deconfinement transition does not change the fact that we had some cycles shrinking at the horizon, while in strong coupling, we know just from geometrical arguments that we cannot have any cycles shrinking at the horizon. So it looks like in all of these cases, which include the backgrounds of Witten, this should be Klebanov-Strasser, and the Sena-Nunez, the deconfined phase actually does not smoothly interpolate between the gravity regime and the QCD regime, and there has to be some phase transition in the middle. And that's, one example where one should actually be very careful in these interpolations between gravity regimes and other regimes, because at least in some cases, it's clear that some order parameters are different in these different phases. Now, the confinement-deconfinement transition, it's obvious from what I said that it's mapped to a phase transition where we form a black hole. One way to analyze these phase transitions, which Eliezer taught me, is to draw the temperature as a function of energy. And then here you have at low temperatures, well, at low energy densities, you have the confined phase, and that phase is stable until you hit the Hagedorn temperature. And when we have a theory with a gravity approximation, then we know that the transition to a black hole always happens at a temperature that's much lower than the Hagedorn temperature. Namely, it happens at a temperature of the order of the characteristic scale of the gravity background, which, as I've mentioned, in order to have a gravity approximation, the characteristic scale of gravity has to be much lower than the string scale, so this temperature is really much lower than that. And in such a case, we know that we always have a first-order transition because it happens at a place where this confined phase is still stable. So we know that whenever we have a gravity approximation, the deconfinement transition is always a first-order transition. Now, we also know that this is not true in general in large N theories. There are examples of large N gauge theories where the deconfinement transition is actually second-order, and then the phase diagram looks like this. And when you heat up, you really get to the Hagedorn temperature and then continue heating continuously. But it looks like if you have a theory that does have a gravity dual, there is what Eliezer and his collaborators called Hagedorn censorship. Namely, if you heat up the system, you always have a phase transition below the Hagedorn temperature. But what I want to emphasize is that this is really just a feature of theories that have a gravity approximation. We know that in highly curved backgrounds that are dual to these types of gauge theories, we know that you can reach the Hagedorn temperature. And of course, another way to reach the Hagedorn temperature is just to somehow superheat this confined phase. And hopefully, someday we'll learn more about how to get to the Hagedorn temperature and avoid the censors. Now, this picture that I gave, of course, maps black holes to just standard phases in gauge theories, so it confirms that black hole evolution is exactly unitary, even though the precise details of how this unitarity is realized seem to be very complicated and in some cases involve summing over many different backgrounds. And again, Eliezer has worked extensively on this. Now, the black branes that I described above are, of course, very far removed from real black holes. In particular, they stress all over space, and they're really black branes. But using very similar arguments, one can also build localized black holes that would not have any non-compact directions. And the way to do this is just to build bubbles of the deconfined phase, which we've argued corresponds to a black hole, inside the confined phase. So you imagine that you have the confined phase everywhere outside, and then in the middle you build some bubble of the deconfined phase. And it turns out that such bubbles are actually stable, at least in many theories, at leading order in large N, and this can be mapped to the stability of these black holes in gravity. So this gives us a way to build real non-compact black holes in the dual gauge theory. And again, coming from the field theory side, it's obvious that the whole evolution of these black holes, their formation and evaporation, is completely unitary. What's actually less obvious on this side is the fact that they're black, namely that when you throw something at them, it doesn't come out immediately, but it only comes out much later and distorted through Hawking radiation. And that seems to be a feature that only shows up perhaps in these special theories which have a weakly curved gravity dual. And we don't really know what's responsible for that. Okay. The next topic I want to discuss is phases with flavor. And well, first of all, maybe are there any questions about the phases of theories with only adjoint fields? Yes, Nadi. Well, these were what I called Coolant phases, I guess. So what's the difference? I mean, what's the limit of the Coolant phase, I guess, where you do some rescaling of the parameters. And for the same reasons, I wouldn't expect to have a stringy dual in these phases, just because you have all these U1 fields moving around, and there's no obvious. Well, I mean, if you're talking about the limit where it's really a free theory, then, of course, well, a free theory of just n U1 fields probably doesn't have any useful stringy dual. I mean, that is just a free theory. Any other questions? Okay, so next I'd like to add some flavors in the fundamental representation. And when we do that to QCD, we find many interesting phases. We have color superconductivity phases, color flavor locking, and so on. Unfortunately, most of these very interesting phases actually disappear when you take the large N limit because, well, for color flavor locking, it's sort of obvious that if you take the large N limit and keep NF finite, there's no possibility of such a phase. And you could also argue the same for color superconductivity. So these... Yeah, keep N flavor fixed, that's right. So that's the only limit that I'll discuss here, although, of course, as we heard yesterday, there are also other interesting limits. But this is the only limit that really corresponds to a weakly coupled string theory, which we can control. So the description of these phases of string theory is going to be interesting, but it has to be very complicated because they don't have a good large N limit, so they're not described by a weakly coupled string theory. And basically, this happens because in the larger limit, with a fixed number of flavors, the effects of flavors are suppressed by an f over n. So the flavors don't really affect the behavior of the gluons. So the gluons sort of do whatever they do, either deconfine or confine independently of the flavors. And adding the flavors is a subleading effect. And in string theory, we see that because to add the flavors, as I mentioned, we have to add some Dbranes, which would correspond to the boundaries of the world sheet, which correspond to the quark loops, basically. And in the large limit, these Dbranes can be treated as probes so that they don't affect the closed string background. They just give some small corrections to it, and they don't affect the gluon dynamics. But even in this limit, it turns out that there is still interesting flavor physics. In particular, you can still have interesting flavor condensates, and you can study mesons, which are open strings that end on these flavor Dbranes, and baryons, which are point-like Dbranes in these backgrounds with n strings connecting them to the flavor Dbranes. So there are still many interesting questions to ask about flavors. So again, we'll go back to Shimon's lecture notes. And Shimon tells us that indeed there is a vast number of questions which one would like to investigate. But I'll concentrate on a particular one, namely Chiral symmetry realization. So I'll do the same in this talk here. And I want to describe here in particular the realization of non-abelian Chiral symmetry and whether it's broken or not. So as I've already mentioned, in order to add flavors to one of the Gates theories, one of the pure adjoint Gates theories that I described before, we have to add some Dbranes. And these Dbranes have to, of course, fill the 4 dimensions of space. And they also fill some manifold. Well, and in the other directions, they can either fill all of the other dimensions, or they can sit in some submanifold of the extra radial direction and any other extra dimensions that we have. And the difference between these Dbranes and the other Dbranes that showed up before is that these flavor Dbranes, because they really correspond to degrees of freedom that are in the theory also at very high energies, they have to stretch all the way to the boundary. So unlike these Dbranes that I mentioned before, corresponding to, say, the Higgs phases, these are Dbranes that extend all the way to the boundary because we really have local operators corresponding to these quarks and anti-quarks. Now, if we want to get a non-abelian Chiral symmetry of SUNF cross SUNF, as we have in QCD, then it's obvious that we need 2 types of Dbranes, one which would we need to have NF Dbranes of one type that would give us the SUNF left-handed, and NF Dbranes of another type that would give us the right-handed SUNF. Now, it turns out that it's actually quite hard to build Dbrane realizations of non-abelian Chiral symmetries. And as I've mentioned, in order to build these string duals, we usually start from Dbrane constructions. So it's quite hard to find string duals of theories that have non-abelian Chiral symmetries. And there's a simple reason for that. And the reason is that if we have a QCD-like theory, then we know that the left-handed quarks and the right-handed quarks are related by parity, which means that the Dbranes of the first type that we add have to be related to the Dbranes of the second type by a parity transformation. But we also know that if we have a space-filling Dbrane, then a parity transformation turns that into a space-filling anti-Dbrane, which is the same as a Dbrane of opposite orientation. And that means that in these backgrounds, we must have NF Dbranes and also NF anti-Dbranes. And whenever we have that, of course, we're putting NF Dbranes and anti-Dbranes together. And that always, and that seems to lead to a tachyonic instability in our background. So that's sort of the basic reason why it's difficult to build backgrounds which have a Chiral symmetry. Now, of course, to some extent, we want to have such an instability because we want to have a Chiral condensate. So we know that there is supposed to be some instability related to the strings between these 2 types of Dbranes that would give us the Chiral condensate. But we need to have this instability at low energies and not at high energies. Well, if we have space-filling Dbranes, anti-Dbranes, then we have this sort of instability at all energy scales. So we need to find some way to get around this problem. And so how do we get rid of this problem? So one possibility is that, when we have high curvatures or large Roman fluxes, then that these could lift the tachyons between branes and anti-branes. So this has been suggested also for other reasons. And presumably, this is actually the mechanism that works in QCD, namely that somehow the QCD string lives in a highly curved enough background that the string between a Dbrane and an anti-Dbrane is not really tachyonic anymore in that background. But we don't have any examples of that mechanism yet. But if we want to stay in the gravity approximation, which is the thing that's easy for us to do, then we can't really invoke this. And in the gravity approximation, we know that the string between a Dbrane and an anti-Dbrane is always tachyonic. So the only thing we can really do is to separate these branes from each other in one of the extra dimensions. So you must have at least one extra dimension. And you must separate the Dbranes from the anti-Dbranes in this extra dimension. And a simple example of this is a model that was discovered by Sakai and Sugimoto 2 years ago. And that model starts from a model of Witten for a confining gauge theory, which involves taking ND4 branes which are compactified on a circle in the x4 direction with antiperiodic boundary conditions. So this is a theory that at low energies, in some limit, gives pure Young-Mills theory, because all the extra Philosophian modes are massive and decoupled in an appropriate limit. And we can take that limit and add to it an FD8 branes which intersect the D4 branes along a 3 plus 1 dimensional surface. So we can have an FD8 branes that intersect these 4 branes at x4 equals 0, and an F additional D8 branes that intersect them at x4 equals L, so that they are separated in this extra x4 direction. And when we do that, it turns out that the string connecting these D branes and anti-D branes, well, it's not tachyonic anymore because these branes are separated from each other. And in fact, when we take the near horizon limit of the D4 branes, all of the apparent instabilities of this background disappear, and we get a picture that's exactly like this, where we have, where the closed string background is just the near horizon limit of these D4 branes on a circle. And in that background, we have asymptotically 8 branes and anti-8 branes, which go to infinity at different positions in this extra dimension. Now, a nice bonus that we get by doing that is that when we have this description, which at first sight seems pretty ugly to have branes and anti-branes together, who ordered that? But this actually gives us a very nice geometrical picture for chiral symmetry breaking, namely these D branes and anti-D branes, which, as I mentioned, are just the same thing with an opposite orientation, can just connect along a curve like this in the interior of space. And this gives a very natural realization of the breaking of chiral symmetry from SUNF cross SUNF to SUNF, basically without doing any computation. You see here that the chiral symmetry is broken in precisely the pattern that you expect. Now, in some cases, you can actually argue that the D branes and anti-D branes have to sit in a configuration like this just by topological arguments. Namely, these D branes, they go somewhere in the U direction, and and then, as I've said, in some cases there are some cycles that shrink when we go down in that direction. And if these 8 branes are, or if these D branes, whatever they are wrapped on a cycle that shrinks, then they could also just end somewhere in the interior. But if these D branes are not wrapped around one of the cycles that shrinks, then basically they can't end anywhere, so they have to connect to one another in exactly this way. So in cases like that, when the D brane is not wrapped on a cycle that shrinks, the chiral symmetry breaking is really just dictated by the topology, so you really don't have to do any computation at all to verify chiral symmetry breaking in the large n limit. And that's exactly what happens in this Sakai-Sugimoto model. So this gives a very different type of argument for chiral symmetry breaking than the ones that we usually use in field theory. So that's the simple case where you can just argue topologically that this has to be the correct phase. If you have a different possibility where the brane wraps a cycle that does end in the interior, then you could also have a phase where just the D branes and anti-D branes go straight down and just end in the interior. And then you have to compare the energies of these configurations and see which one wins. But it's not clear if such a possibility can really happen. There are certainly no examples of this. And we know that in the large n limit, chiral symmetry breaking is really dictated just by basically anomaly matching considerations. So it seems like probably in all backgrounds that realize the chiral symmetry, it must be the case that this this picture is the correct one and that it follows just from the topology. Otherwise, as already pointed out long ago by Amati and Eliezer, string perturbation theory would have to break down in order to have such a phase where the chiral symmetry would be unbroken in the large n limit. So this was the description of chiral symmetry breaking at 0 temperature. When we go to finite temperature, then in the confined phase, having a finite temperature doesn't change anything. But in the deconfined phase, there's a big difference because the D branes can now end on the horizon because in Euclidean space, the horizon, in the horizon, the Euclidean time circle shrinks to 0, and the D branes are certainly wrapped around this Euclidean time circle. So in this deconfined phase, we have 2 possible configurations. Either the D branes end at the horizon, or they still connect and break the chiral symmetry. And you have, in order to see if the chiral symmetry is broken or not, you have to compare the free energies of these 2 configurations. And yeah, this is very easy to do when you have a gravity approximation for your string theory. It's just a classical mechanics question, more or less, to compute the energies of these configurations and compare them. And this is an example where a question which is very hard in large MQCD becomes very easy in these gravitational dual descriptions. And if you compute these phase transition temperatures, you find that in some cases the chiral symmetry breaking transition happens together with deconfinement, as also seems to be the case in large MQCD. And in other cases, it seems like the phase transitions are separated from each other, so it looks like there are no general arguments about relations between the chiral symmetry breaking and deconfinement transitions. Sometimes they're together and sometimes they're not together. Now, which other flavor phases can we have at large n? So I'll just very briefly discuss that. In large NQCD, if we have a large or in QCD in general, if we have a large baryon chemical potential, we know that the quarks fill a Fermi sea, and for a large chemical potential, that Fermi sea has a very high Fermi level, so that the physics is perturbative. And then you can just do perturbative computations and show that the naive vacuum is unstable towards forming particle-hole pairs with momenta of order of the Fermi level. This is what's often called the DGR phase. And it's not clear really what's the endpoint of this instability in large MQCD. Maybe some sort of Chiral crystal or some more complicated phase. So that's an active well, that's a question of active investigation among QCD people. I should emphasize that usually in QCD you expect that quark pairs would form when you have baryon chemical potentials, but in fact at large n, such formation of a quark condensate is suppressed because it comes from a non-planar diagram, so you really have a different type of condensation in these large n limits. And it would be very interesting to study this type of questions and the gravity approximations. So when we have the gravity approximation, we don't have this. When we have a gravity approximation, of course, our field theory is no longer weakly coupled even at high energies, so we don't have this type of simple perturbative analysis that tells us which condensates we'd like to form. But on the other hand, we have the gravity that's supposed to tell us what the answer is, so it would be interesting to study analogous questions in the gravity approximation. And as I mentioned, to study other phases that exist in large N QCD, it seems like these other phases disappear in the large N limit, so we have to study them, including 1 over n effects or even finite n effects, which means that we have to go beyond classical string theory and study all quantum string theory or quantum gravity. And of course, we can also turn that around and say that since we know that these types of phases exist at finite n, we can use them to learn things about quantum string theory or quantum gravity. And again, it would be interesting to see what we can learn from that. So I'd like to end by listing some number of future directions, which are still completely open questions in this field of string theory and gauge theory. So of course, we've made a lot of progress in the last 40 years, I guess, since it started, and particularly in the last 10 years, but there are still many open questions. Of course, one obvious open question is to actually find the string theory dual of large N QCD. So we know how to do that in principle. As I've described, we know some string theory backgrounds which interpolate between the background for which we know how to write down the world sheet theory and the QCD string. So in principle, we just have to write down the world sheet theories of these strings, solve it as a two-dimensional quantum field theory, change these dimensional parameters, and see what we get. But of course, in practice, that's very hard because these world sheet theories describe sigma models that are very highly curved and have remote backgrounds. So even the classical string theory, which is what's relevant for the large N limit, is very complicated, and so far not much progress has been made. But hopefully some progress can be made, perhaps using integrability. We'll hear from Igor in the next hour about some very impressive progress that's been done using integrability for n=4 gauge theory. In large N QCD, it's not obvious that there is any useful notion of integrability, so it's not obvious that the same methods will be useful also in QCD, but one can hope that perhaps there is some integrability of some other type that we don't understand yet, and that could be useful for solving these sigma models. If we cannot find any exact methods to solve large N QCD, then it's, well, perhaps one can try to study numerically these strongly coupled two-dimensional gauge theories, and then try to use numerical simulations to study the string dual of large N QCD. And it looks like that should be, of course, if you're doing numerics, you could also just do lattice QCD and solve the theory directly, but it seems like doing these types of numerics should be much easier than lattice QCD. For one thing, it's a two-dimensional gauge theory, not a four-dimensional gauge theory. Sorry, two-dimensional theory, not a four-dimensional theory. And of course, also, if you try to do lattice QCD at large N, then the number of, well, then you need to spend a computer time of order n cubed. Well, here the computer time is order 1 in the large N limit, so this should certainly be an easier way to solve large N gauge theories numerically. And also, we know that lattice QCD is somewhat limited in the types of questions that you can answer using it, because you're limited to Euclidean spacetimes and so on. And it's plausible that on the world sheet you would have less limitations, so you would be able to answer numerically a different set of questions. Now, so far in this talk, I hardly mentioned supersymmetry, except when I discussed this gravity approximation, where we always have an approximate supersymmetry whenever we have a weakly curved background. Of course, well, one aspect of supersymmetry is when I talked about the phase structure, I only talked about some order parameters, but of course, whenever we have a global symmetry, like supersymmetry, we can always discuss whether it's broken or not, and so that's obviously another interesting distinction between phases of gauge theories, which has its mirror in string theory, as we heard, for instance, yesterday in David's talk. Now, in standard string theory, supersymmetry is actually known to play a huge role, and there is a theorem, more or less, by Kutashov and Seiberg, that tells us that if you have a string theory that has a high energy Hagedorn spectrum, then that spectrum either has to be asymptotically supersymmetric at very high energies, or just by modular invariance, you can argue that the theory must have a tachyonic instability. And now, and it's not clear how this very general argument is avoided by the QCD string. So of course, in the QCD string, we know that in the large N limit, well, we have a Hagedorn spectrum, but that Hagedorn spectrum is purely bosonic because the theory doesn't have any fermions. And in the large N limit, we have just glue balls, and if we have some flavors, also mesons, but we don't have any fermionic states. And on the other hand, we of course believe that large N QCD does not have a tachyonic instability. and that's also confirmed by lattice simulations. So it's an interesting question, how is this instability avoided in the QCD string? One possibility is that the Ramon-Ron fields in the background, which were not considered by Kutesov and Seiberg, perhaps could save the day. Another possibility is that having large curvature could help, because Kutesov and Seiberg assumed that the energy on the world sheet is proportional to the square of the momentum in spacetime, and that may not be true in highly curved background. A more pessimistic possibility is that perhaps the QCD string necessarily always involves some strong coupling, as we would get in a background that has NS5 branes. And in backgrounds like this, even though we have a 1 over n expansion, the coefficients of 1 over n actually diverge in some places, so that the larger limit is not really very useful in the sense that it's not really a classical limit. So that, of course, would be bad news for this program of relating string theory to large n Gates theories, but we don't know yet whether... that's what that would imply, and well, it's possible that in some things the large n expansion does break down, and again, we have examples where that happens, of in these backgrounds that do have NS5 branes, and then we know that exactly that happens, and I think we don't yet know if it happens in QCD or not. No, a simple example is just this n equals 1 star theory in its confining background, that is just n equals 4 Young Mills in a background where it confines, and we know that in that background the large n expansion breaks down because of the presence of NS5 branes. So that is an example of a simple 4-dimensional confining Gates theory where we know that the large n expansion breaks down. And I don't think we have so far any good arguments to tell us if that would happen in the QCD string or not. And of course, it's interesting to find them, as I've tried to emphasize. On my final slide, I'd like to talk a little bit about how could we possibly connect any of this to experiment. So, well, one way to connect to experiment is to solve the QCD string and then try to learn things about QCD. But of course, that's going to be rather difficult, because even if we solve the classical QCD string, that gives us the large n theory. But to connect to real experiments, we have to do the 1 over n expansion. And in particular, many quantities get corrections of order n f over n in QCD, which are not obviously small. In fact, they seem to be of order 1. So it's not obvious if we're ever going to really be able to connect these string theories to experiments in QCD, unless we can really somehow sum up this expansion in an f over n, which certainly goes beyond just the classical string theory. Or alternatively, we might find some quantities which actually do not get corrections of order n f over n. There are certainly some signs that perhaps some quantities in QCD do not get corrections of order n f over n. And then for these quantities, we should be able to directly connect the QCD string to experiment. Another possible way to connect to experiments is to analyze general features of strongly coupled theories. There's been a lot of work in the last few years about studying general features of the strongly coupled quark-gluon plasma that you get when you have a gravitational dual, and comparing that to the strongly coupled plasma that you get in QCD at temperatures that are slightly higher than the deconfinement temperature. And it seems like many general features do behave in a similar way between the theories that we know how to analyze in string theory and real QCD. So that's certainly a useful arena for making contact to experiment, although by its very nature, this type of contact is limited to sort of qualitative questions, and it doesn't seem likely that you could ever quantitatively really compute aspects of the quark-gluon plasma in QCD by these methods. A way in which we may connect not to experiment, but perhaps to lattice QCD, is to try to analyze, to consider the effective action on the QCD string. Now, of course, experimentally, that's very hard to access, because in the real world, the QCD string breaks by formation of 4 anti-quark pairs. So it's hard to access experimentally, but on the lattice, we can just simulate a pure Gates theory without any quarks, and we can try to measure the effective action on the QCD string by lattice methods, and then we can try to. And then the question is, are there any constraints on the low energy effective action on this QCD string that come from the fact that we know that it's embedded in a real superstring theory? And so far, no such constraints are known, but it's conceivable that there would be such constraints which would at least connect this program to lattice simulations. And one final possible way, well, not final, but I'm sure there are many more, but one additional possible way to connect to experiment is that we know that some of these weakly curved backgrounds that I described do give us various confining Gates theories, which are very different from the types of confining Gates theories that were considered in the past. And it's possible that some of these confining Gates theories, which, as I've said, are very easy to study in string theory, could actually appear somewhere at higher energies in the real world. For instance, they could be technicolor theories, or they could be hidden sectors. For instance, the sector that breaks supersymmetry could be one of these weakly curved backgrounds, for all we know. We don't really know anything about it so far. And that, of course, would be a possible spectacular way to connect string theory to high-energy physics, assuming, of course, that one finds some information about either technicolor or whatever hidden sectors there are at the LOC or at future accelerators. So I hope I've convinced you that even though we've made a lot of progress about large N Gates theories and string theory, there's still a lot to do. and hopefully Shimon and Eliezer will continue contributing to the developments in this field also in the future. So thank you.
Time for a couple of questions.
Ofer, you said that